Okay, so next I have 14.19, and that's asking, on a frictionless horizontal air track, a glider oscillates at the end of an ideal spring of force constant 2.5 newtons per centimeter. The graph in figure 14.19 shows the acceleration of the glider as a function of time. Find A, the mass of the glider, B, the maximum displacement of the glider from the equilibrium point, and C, the maximum force of the spring exert on the glider. And then I'll show you the little figure that it gives us. I don't know if you can see that right there. There it is. Because I'm going to be extrapolating things from that. But let me see. So, like I said, A is asking us the mass. B is asking us max force, I believe. Sorry, max displacement. And then C is asking us max force. So, and it is given to us that the period is T equals 0.2 seconds and then K equals 2.5. So knowing this, I'm going to plug it in to our angular, what we know to be angular, which is T over 2 pi, which will equal 0.2 over 2 pi, which will equal 31415. And then for our angular frequency, that equals root K over M. And so we know that So we know that 0.31415 equals root 2.5 M, and M is what we're solving for. So after doing some rearranging and solving for M, I got that M equals 25.33 kilograms. And I'm going to be using this in part B and in part C. So in part B, I will be using the equation that the max will equal negative K over M times X. And we're going to be looking for X. And so from the graph that I showed you, we know that the max is 12. So I get 12 equals negative 2.5, and then we use the mass from part A, 25.33 X, and then I just solve for X, and I get that X equals 121.58. And then finally for C, I'll just do that right down here. I'm going to be using the equation F equals mass times A. And so use max acceleration in known mass, and we get that F equals 25.33 times 12, which will equal 303.96. Or if you just round up, it's 304.0.